So consider this problem. I have a beam, a Euler-Bernoulli beam, like you have done in your strength of materials courses. So this yellow thing is the beam, which is subjected to end moments ma and mb. Obviously, from equilibrium, ma is equal to mb, and I now take the contour along this dotted line, which is infinitesimally close to the boundaries of the beam, but just inside the beam. So that is my delta V, over which I am going to evaluate my JK. So for this beam, let us just recapitulate the assumptions that are made in the Euler-Bernoulli beam theory. So this beam bends when subjected to these moments. It will bend into an arc of a circle, and the radius of curvature is given by kappa, which is del square u 2 del x1 square. Remember, the derivative was del this. V in our case is u2, and this is del x1 square. So this is the radius of curvature of the beam, which we call kappa, and we can write it as u2 comma 1 1. Okay. We also assumed in Euler-Bernoulli beam theory that the strains are zero at the neutral axis. We assume that this beam has a square a rectangular cross section. So it is zero at the neutral axis and then increases linearly with x2 as you go up or down, and therefore epsilon 1 1 is kappa x2, kappa times x2, and uh, then we have uh, epsilon 1 1 is u1 comma 1. So u1 comma 1 is kappa, which is u2 comma 1 1 into x2, and the only stress component is, there are no other strains, all other epsilon ij are equal to 0. So the only stress component that you have is sigma 1 1, which is therefore related to epsilon 1 1 by E times epsilon 1 1. So these are the two relations that we will use for the Euler-Bernoulli beam theory, and they just follow from your usual beam theory equations that you have learned in your strength of materials, uh, just written in tensor notations. So now also you remember sigma is equal to my by I. By sigma we meant sigma 1 1, because that's the only component of strain. The moment is a function, moment can be a function of x1, y is x2, and divided by I, which is whatever the I is for the cross section. In case of a rectangular cross section, it's 112 BH cube. We know this. Now okay, recall that Jk is over del V B Kj Nj ds. Now this del V is the dotted contour in in this beam, which runs inside the beam but infinitesimally away from the boundaries of the beam. So that's the contour that we are looking at. So this contour now consists of four parts. A and B are the ends, left end and the right end. C and D are the top and the bottom parts of the contour. So we will evaluate it separately on these four parts. So on the so we will calculate J1 first. So calculate J1, which is going to be B1J Nj, and remember BKJ is equal to W so that B1J will be W delta 1J minus sigma Ij U I comma 1. This is what B1J is going to be, and when you write B1J Nj, you get N1 minus sigma I1 . sigma I, sorry, uh, sigma ij u I comma 1 nj. This is what you will get. Now, on A, on this phase, n is minus 1, 0, 0. On B, n is 1, 0, 0. So only n1 is non-zero, n2, n3 are 0. Therefore, wn1 is equal to either w or minus w, depending on whether you are on A or B. On A, it is minus w. On B, it is plus w. On the top and the bottom, n here is 0, 1, 0, and here is 0, minus 1, 0, which means n1 is 0 in both cases. Therefore, this term does not appear in case of C and D. What about the next term? In the next term, on A and B, n1 is equal to 1 or minus 1, and therefore j can take values 1. So you have u sigma I1 ui comma 1, whereas on the top and the bottom, n2 is non-zero, 1 or minus 1, and n1 is equal to 0. Therefore, j can take values 2 only. So you have sigma I2 ui comma 1, and this negative sign comes because of whether you are looking at the top or the bottom, right or the left. Okay, so this is the top and this is the bottom, this is the left, this is the right, and here sigma I2, there's no sigma I2 component because sigma 1 1 is the only component of stress in this Euler-Bernoulli beam theory. So therefore this term goes to 0, this term goes to 0 as well, and we are left with, since sigma 1 1 is the only stress component, I has to be equal to 1. So we are left with W minus sigma 1 1 U1 comma 1 at evaluated at A, and W minus sigma 1 1 U1 comma 1 evaluated at B. So now what we will do is we will evaluate this at an arbitrary cross section somewhere here. We call that the cross section X. So at X we will evaluate it, and then if you evaluated it some arbitrary cross section X at a distance x1 from the origin, if you evaluate it at X, you can just use that expression to get the value at A and B. We will do it that way. So W, as we know, this is an elastic beam. So W is half sigma ij epsilon ij for an elastic beam, elastic system, and only sigma 1 1 is present. So sigma 1 1 epsilon 1 1. Epsilon 1 1 we have already found out. So sigma 1 1 in terms of epsilon 1 1 is this. Epsilon 1 1 we know is kappa times x2. Using that, and kappa we know is u2 comma 1 1. So using that, W comes out to be E by 2 u2 1 1 square x2 square. This is a very easy calculation. So you have it at any cross section. It is equal to m square minus 2ei. You evaluate it at A, it is minus ma square by 2ei. Evaluated at B, it is mb square by 2ei. Since ma and mb are equal to each other, are equal and opposite to each other, this is equal to 0. So J1 is identically equal to 0 all over the beam, just as we expected, because the beam does not contain any discontinuities. If you calculate, if you try to evaluate J2 and J3, you can similarly see, and I leave it as an exercise, you can similarly see that J2 and J3 are 0 as well. So all the J's are 0. In fact, J2, J3 are 0 almost trivially. only J1 you have to prove that it is indeed equal to 0, and all three turn out to be 0. Let us turn to the second problem now, where we have the same beam, same contour. So this is the del V. It is now under tension. So we have put it under tension. So sigma applied on both sides under tension. And the beam is now made up of two materials, A and B. And there's a line of discontinuity here. So there are two materials, and your uh, domain actually spans through the discontinuity. So the discontinuity lies within the domain. So as in the previous problem, we again evaluate J1 in exactly the same way, A, B, C, D, and we know that the contour integrals on C and D are equal to 0. So you will be left with the contour integrals on A and B only, and that's what we have written right away. In this case, again, sigma 11 is the only component of stress. So sigma 11 U1 comma 1 is what appears here, just like in the Euler-Bernoulli problem, but the sigma 11, the expression for sigma 11 is now different. So sigma 11 is given by sigma 11 times A is the cross-sectional area, not this A. Sigma 11 times this cross-sectional area gives you the total force P, and W is equal to P square by 2 AE for a beam under tension, for a bar under tension. Epsilon 11 is U1 comma 1 is P by AE, and all other epsilon ij are equal to 0. So you plug this in for, again, arbitrary cross section. So if you plug this in for an arbitrary cross section, just like we did in the other case, then W has been already evaluated, and you can easily show that this integral is minus P square by 2AE. However, E is different on two sides. So if you evaluate this at A, it will be P square by 2A 1 by EA, and at B it is 1 by EB. Therefore this J1 is not equal to 0. This is not equal to 0 because your domain now spans through this line of discontinuity. So what we have shown basically is that this Jk, this quantity Jk, which is defined on the basis of the energy momentum tensor, this quantity Jk that we have defined, this quantity is a quantity that is sensitive to discontinuities in the displacement. So if you have defects that cause discontinuities, then this can pick it up provided the discontinuity lies within the delta V. If the discontinuity lies within delta V, this will return a non-zero value. Otherwise, it will return a zero value. So this is a very clever integral that is sensitive to discontinuities which cause discontinuities in displacement. So this will be also sensitive to the existence of a crack tip. And in the next part, we will show how this can be rigorously proved.